Okay, so as always, let's talk about what you are going to find out in the next 3 weeks. And I don't know how many of you actually look at this. Does anyone actually look at this like right before the test?
Yeah.
You do? Does it help?
Yes.
Okay, like you go through and go, oh yeah, I know that, I know that, I know that. Oh, what's you talking about here? I don't know that, right? You might even want to consider, on every day or every second or every Thursday, have a look at that going, oh yeah, that's how much we've covered. Okay, yeah, I know what you're talking about there. Maybe take a more active part in what's going on. Because I will tell you this, if your whole idea of studying is just to try to figure it all out and cram it in the night before, that's going to get progressively harder and harder and harder. Anyone run the marathon with Mr. Smith in the Marathon Club last spring? Anyone in here? Nobody did? Okay, well I know I'll pick on that because I don't run. So when your mom gets ready to go run a marathon or a half marathon, does she go out and run a whole bunch the night before, hoping it's going to help her the next day? No way, because that would be, or stupid might even be a good word for that, right? And yet that's exactly what students do when it comes to studying. You might hear me say you got to run the miles. It's the same idea. If you're going to run a half marathon, you better put in 12 weeks worth of work. So keep that in mind as you're getting ready for this next test. So students will define the gravitational force constant as G is a force per unit mass in newtons per kilogram, and the weight is Fg or Fw is mg. The acceleration due to gravity is derived from Newton's laws and determined in the laboratory. Students describe the normal force in terms of the mutual attraction of masses and draw simple free body diagrams. Student will be able to define the gravitational field qualitatively. What does the word qualitatively mean? It's a big fancy word. You guys know the difference between qualitative and quantitative? Quantitative has numbers. I'll give you an example. The weather today, the temperature is -3. If I said the weather today is, it's okay, it's not bad, it's nice, that's a qualitative description. Okay, so you're going to define gravitational field qualitatively without words as the region of space around a mass where another point mass experiences force. How long should that take me to cover? Wait, here's the part where you do some learning, which means listening. How long should it take me to define that for you?
30 seconds.
If that, I think I've already done it. We can almost do this. I will cover it again, but technically, if you've been listening, there we go, check, done. Define the field qualitatively as the region of space around a mass where another point mass experiences force. I'll come back to that, don't worry. Diagram the Earth's gravitational field using lines of force. I'll show you how to do that. Define the gravitational field quantitatively as a force per unit mass. There, I just did that one. We've done 2 out of 12 already.
Wow.
Well, whatever the number is, I don't know. Compare and contrast the terms mass and weight. What does that mean? Compare and contrast. It's fancy words for find the similarities and find the differences. So you need to be able to do that. Describe qualitatively and quantitatively apparent weight changes in vertically accelerating systems. In other words, tell me what happens to your weight in an elevator. We'll talk about that. Derive the acceleration due to gravity from free fall and Newton's laws. To be brutally honest, I'm not even sure what that means. It's so simple. Perform an experiment to calculate G near the surface of the Earth. Oh yes, so remind me to go and grab the G ball down and see if the battery is deep place. Are you with us there, Chloe? This is important, man. It's like going to practice. Same idea. Practice sucks.
Yeah. Games are fun.
Well, I guess there's always family fun you can play. Yeah, score a lot of goals too. If that's all you want to do. Solve free fall problems. Think I'm going to spend a lot of time on that?
Probably.
Yeah, probably, yeah. Describe terminal velocity both qualitatively and quantitatively. Define the coefficient of friction mu is the ratio of the force of friction and the normal force. There, it's all it says is define. I can check that off. Distinguish between static and kinetic friction. Compare the effects of the normal force materials involved, surface area, and the speed and the force of friction. And solve problems with the coefficient of friction for objects on a horizontal surface. There is a lot in this unit, isn't there? A lot of it is small, though. Okay, so one of the things that I've learned lately, actually I've known this, it's been reinforced for me recently, is that you come into this room with misconceptions, things that you already believe, and now it's my job to sort of, well, tell you that you're wrong. Okay? So let's see what you know. Go grab a clicker. A little pre-quiz. I'm not talking about the vacuum cleaner. No, I'm not talking about vacuum cleaner. I'm talking about like the vacuum of space. Vacuum of space, not the vacuum cleaner for your carpet. Oh my goodness. That's what I thought. Come on, Cameron. Stay with me. Good. Number 2, NASA has built a zero-gravity chamber. A zero-gravity room. Gravity is the same as air pressure. Gravity is the same as air pressure. Number 4, gravity pushes down. Oh, you guys are going ahead on me. Gravity pushes down. Gravity is the same as magnetism. Gravity in space is 0. Everyone's finished. During a full moon, the moon has a higher gravitational pull, creating a higher tide. True or false? You guys know what a full moon means, right? What weighs more, a pound of feathers, pound of bricks? They're the same, can't tell without the volume. Yeah, here's where Kahoot would be good, right? Where have you played that? Oh, yeah, nice. Black holes don't suck everything into them. Read it carefully. Black holes don't suck everything into them. And the last one, number 10, which of the following diagrams most closely represents the gravitational forces that the Earth and the Moon exert on each other? Note that the mass of the Earth is about 80 times that of the Moon. Apparently Siri thought I was talking to her. That's weird. Come on, you guys. Okay, let's see how you did. That's the last one, right? Well, how'd you do? Well, the overall average is 47%. Wow, you've got a lot of misconceptions to deal with here. Or maybe your reading skills aren't as good as they should be. Okay, well, let's just check the answers here. There is no gravity in a vacuum. Completely false. What do you think is holding the moon in place around the Earth? The gravity of space outside the Earth is space, right? What do you think is holding the moon? That's about the size of the moon. What do you think is holding the moon in orbit around the Earth? Gravity! There is gravity. So that, of course, is false. NASA has built a zero-gravity chamber. Well, that is false.
How are we supposed to know that?
No. Remember, these don't count for anything. It's just getting me started thinking about gravity. Where do they train the astronauts? In that spinny thing. Solid spinner? Oh, they do. Yeah, they practice that just for simulating gravitational effects from them. They do go underwater. They got a big giant pool. I heard someone saying it's that plane, right? You know what it's called? It's called the bomb pump. It's a big plane that goes up like this and comes down, right? So it's not necessarily a zero gravity chamber, but it's a plane, right? Yes. Yeah. And they do a lot of work underwater, and I'll show you some videos. Gravity is the same as air pressure. Yay! Almost everyone got it right. That, of course, is false. It has nothing to do with that. That's just sort of made up. Gravity pushes down. Well, it's false because gravity pulls down. Little English trick there. Apologies to the international students. Gravity is the same as magnetism. False. Nothing to do with it. In fact, magnetism can pull and push, but gravity can only pull. Gravity in space is zero. That's the biggest misconception there is. What's that? Because of gravity? Oh, okay. Yes, everything orbits the sun because of gravity. And everything orbits this Earth. All those satellites that are doing your GPS are all orbiting because of gravity. There is a lot of gravity in space. And I will talk about why it looks like there is no gravity. During a full moon, the moon has a higher, oh my God, has a higher gravitational pull, creating a higher tide. Okay, let me explain. When we get a full moon, you guys know the difference? Like, there's like quarter moon, and then there's like half moon, and then there's like 3/4 moon, and then there's full moon. When there's like quarter moon, where's the other 3/4? Still there, you guys. It doesn't go away. It doesn't disappear. It's not like my hairline. It's still there. You just can't see it. That's like my hairline. Okay? Yes. The same amount of gravity. Oh my goodness, you guys. Can't believe that many people said true. Now, it is true that sometimes the moon is closer to the Earth. In fact, I think the full moon that's up this week, I think, is considered to be a supermoon. You know what a supermoon is? When the moon is slightly closer. So when the moon is slightly closer to the Earth, then you do get slightly higher tide. Question, Dave?
I was asking the word.
What?
The word.
Supermoon. Oh, gotcha. Good one. Good one. Did you know that a lot of people attribute Galileo to gravity and stuff, but it was actually the indigenous people of Australia that first realized that the moon and the Earth's tides were related. I just recently found that out, so kind of interesting. What weighs more, a pound of feathers, a pound of bricks? They are the same. Oh my goodness. Anna, read the question. You forgot to. Black holes don't suck everything into them. Well, that, my friends, is true. Because if it was false, guess where you would be? In a black hole. Right? Here's how, I'll give you the quick and easy version of what a black hole is. Okay? So a black hole is simply a star that has collapsed on itself. Right? Collapsed down on itself to such a small point you can barely even understand it. It's that small, it's that dense. Okay? So what was orbiting that star to begin with? Planets and other things, right? And so when it's now a black hole, what is now continuing to orbit? The same planets. Now they're just orbiting something that's a whole lot smaller. In fact, that's how they determine where black holes are. They look for planets that are orbiting nothing that they can't see. And they say, oh, that's because the black holes, etc. Okay? Black holes only suck things in that would that enter into their sort of gravitational space anyways, right? So, like, if a meteor was to crash into it, if it's a black hole now, oh, too far. If it's a black hole now, and it was about to crash into where it was before, if it goes beside it, then it's still going to enter into it. Okay, so it only sucks things in that would have crashed into it when it was in its large form before. That's the black hole. Among other things. Okay, now here's the big one here. Let's see how many people got this one right. Because this is a question from the last unit. You all should get this right. And the correct answer was C. This one right there. Which of the following diagrams most closely represents the gravitation that the Earth and the Moon exert on each other? Note that the mass of the Earth is about 80 times that of the Moon. Okay, so here's the Earth. Here's the Moon. We can say this is about 80 times. There's about 80 of these in here. Maybe it needs to be a bit bigger, right? Regardless. Why is it C? Who got it right? Why is it C? Tia?
Because you have to have the same force on.
Newton's third law says what? Equal and opposite. Equal! You guys do know what equal means, right? What does equal mean? The same. And so the gravitational force on the Moon is the same as I think I'm going to have to start taking them away, you guys. I really do. Because some of you just can't. I get it. I was at a conference that was really, really, really boring at times. And I will admit, I pulled my phone out. Pardon me? I didn't play any games. No. In fact, more often than not, I was looking at some of the Twitter feeds from other people, what they were saying about the conference. Pardon me? No, I was not. In fact, there was a lot of adults. I saw people sitting there checking their email and doing a lot of things. I actually walked out on one as well because it was incredibly boring. I get it. I don't think I'm that boring. Pardon me? No, I think I'm doing a way better job of entertaining you than that lady was doing on Saturday afternoon at 4 o'clock talking to me. It was very tough to follow. I felt bad for the lady that was going to follow her. I thought she was going to rip my head off because I walked out the door. I ran. I will admit that. She was a scary looking lady. What was I saying? Oh yeah, that was equal and opposite, right? Okay. Where was I? What was I saying? Yeah, equal and opposite. I was on the right track or something. Oh yeah, I said that. But then what else? What you did to me, Henry?
Talking about meteors.
Oh yeah, unity, right. Why, if they're equal and opposite, how come the Earth doesn't rotate or orbit the moon? Well, because the moon is small, right? So the same amount of force, but there's different accelerations. How come? Bigger mass means? Bigger mass means small accelerations. Small mass means big accelerations, which is why the small things orbit the big things. But the gravitational force between them is the same. Think that's going to come back to bite you at some point?
Probably not.
What I'm really saying is, think that's going to appear on the test in some form? Possibly, yes. Okay, so that's all with that. So, first of all, let's look at a white cow in a snowstorm. Okay, so, anyone been to Pisa in Italy?
Yeah.
Travel club? Okay, well, you've all probably heard of the Leaning Tower of Pisa. The story is that Galileo dropped a heavy iron ball and also a lighter ball, and Aristotle would have said that which one hit the ground first? The heavy one, the iron one, right? No one bothered to actually go and do it, which is a surprise. Mr. Burnett, okay, right?
Just learning.
Oh, just learning. Okay. So, anyone know Jake Rampton? He made a video for me. So you're playing song? Aristotle, the ancient Greek dude, wore the bed sheet round, right? Would have said that the ball that this is, what would you say? How much heavier is the big one? Like 5 times, 8 times maybe? Probably something like that, right? He would have said this one would have landed 8 times faster than this one. How can, like, in all those thousands of years, no one took 2 rocks and went like this and dropped them? My guess is likely it happened, but Aristotle had such a reputation that no one dared to go against him. Okay? But yeah, exactly the same time. Okay, let's do some reading here. Okay, here's the actual explanation. Were you videoing me up there too, you guys? Were you doing that? I saw some people have their phones out. Or you were just pretending to and just checking Snapchat, yeah. Alright, so Galileo showed that falling objects accelerate equally, regardless of their masses. This is strictly true if air resistance is negligible. Now that's a word we're going to use a lot. What does the word negligible mean? It's like the amount of shampoo I use in a week. It's negligible.
Not 0?
Pretty much 0. So small that it might as well be 0. Every once in a while I do it just to see if I can still remember how to shampoo my hair. It is approximately true when air resistance is very small compared with the mass of the falling object. For example, a 10 kilogram cannonball and a 1 kilogram stone drawn from an elevated position at the same time will fall together and strike the ground at practically the same time. The experiment said to be done by Galileo from the Leaning Tower of Pisa demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than a lighter object. Galileo's experiment and many others that showed the same result were convincing, but Galileo couldn't say why the accelerations were equal. The explanation is a straightforward application of Newton's second law, and is the topic of the cartoon Backyard Physics. Let's read several here. So you flip the page over. It's one more of those cartoons that isn't very funny. It's up here as well on the screen. Many of maybe you may not be familiar with this clothesline thing, but anyways, there's this person here, a lady, and she's got a clothespin in her one hand and a bag of clothespins in the other. And she says to the 2 kids, if I drop the bag of clothespins and the single pin at the same time, which will fall to the ground first? And the one kid says, that's easy, the bag of clothespins is heavier. Is that true?
Yeah.
Trent?
You drop a dog.
Oh, let's get to that. Hang on to that question. Hang on to that question. The bag of clothespins is heavier, which means gravity pulls on it with more force. Is that true? Is the bag of clothespins heavier than a single clothespin? Well, that part is true. Does that mean that gravity pulls on it with more force? Yes. More gravity, more force. So the bag of pins will accelerate more and hit the ground first. Is that part true? Well, let's say question mark. The other kid says, not true, the bag of clothespins has more mass. Is that true?
Yes.
Yes, which is to say has more inertia. Is that true? More mass, more inertia?
Yeah.
That is true. It will be less responsive to gravity and lag behind the single pin. Just like it's really hard for a train or a big semi to get up to speed, big mass, big inertia, really hard to get up to speed. He's saying that the big thing will just kind of hang in the air before falling. He says the single pin will hit the ground first. So, first part is true, second part is true, we're not sure about the third part. She drops them, says, sorry gang, tied score, how come? She says, since the bag has both a greater weight and a greater inertia, one offsets the other. So the big weight divided by the big mass is equal to the small weight over the small mass. And the accelerations are what we call g. And what is the value of g here on Earth? What is the numerical value of g? 9.8. Okay, and it's just like for every kilogram of mass, the scale is going to show how many newtons? For every kilogram. If I have a 1 kilogram object, I put it in the scale, it's going to show 9.8 newtons. If I'm 100 kilograms and I'm not, it's going to show 980 newtons. It shows 840 newtons. How much do I weigh? What is my mass? If it shows 840 newtons, what is my mass? Divide by 9.8. Go ahead, tell me, what's my mass? Anyone? You know what? Let's leave that for the next time.